For this project, we wanted to determine the acceleration of the model toy rocket car. So what we did is we took 3 different cars which weighed 3 different amounts, and these would end up resulting also being our manipulated variables. So the first car that we tested weighed 0.297 kilograms, the second one weighed 0.579, and the third one, the heaviest one, weighed 1.457 kilograms. So what we did to create these cars is we strapped a model rocket engine, this thing right here, to a makeshift car which we made by ourselves. So one at a time we took each car and we fired it to see how fast it would go in terms of acceleration.
For all 3 of our cars, we have the same free body diagram. On the free body diagram, there's a normal force, a force of thrust, a gravitational force, and a force of friction. Because the force of thrust is so large, it overcomes the other 3 forces, which are, as a result, we are disregarded.
This is test 1, weight 297 grams with no additional weight attached, and we're going to calculate with what force this car will accelerate. Take 1. 3, 2, 1.
The information gathered from the video just shown shows a car traveling 17.61 meters in the time frame of 1.95 seconds. The initial velocity of the car is 0, the final velocity we do not care about or wish to calculate, therefore we can calculate for the acceleration. The work for calculating the acceleration is shown in the area here. The final acceleration comes out to be 9.26 meters per second squared. Now that we have this, we can calculate the force of thrust applied on the car using Newton's second law. The car weighs 0.297 kilograms and the acceleration of the car is 9.26 meters per second, and the final thrust comes out to be 2.75 newtons. This may seem like a low number, but this is 2.75 newtons worth of force being applied to the car constantly.
Okay, this is test number 2. Car weighs 579 grams now. We almost doubled the weight, so now we're trying to see if the force that the car accelerates with is almost cut in half because it has double the weight. So test number 2, we'll see how it goes. 3, 2, 1.
In the video just shown, the car traveled 11 meters in 1.6 seconds with initial velocity of 0, and the final velocity was irrelevant, so we did not calculate it, and we calculated acceleration. Here's our work shown for calculating acceleration, which led out to be 8.59 meters per second squared, and then we used Newton's second law to calculate force of thrust, and the mass was 0.579 kilograms and the acceleration was 8.59 meters per second squared, which led to a force of thrust which was 4.97 newtons of constant thrust.
Okay, test number 3. This car weighs 1,457 grams. So we almost added another 1,000 grams to what we initially started with. And so we're just going to see what the result is this time.
How does that thing go off?
You have a detonator right here.
Did you make it?
Yeah.
What grade are you in?
Grade 11.
Do you have to make it?
Yep. 3, 2, 1. Oh, yo, it's lit on fire.
From the video shown before, the car traveled 15.5 meters in a time frame of 2.01 seconds. The initial velocity of the car is 0, and because we did not wish to calculate the final velocity, we decided to calculate the acceleration. The work for the acceleration is shown here. The acceleration comes out to be 7.67 meters per second squared, even though it is not shown on the page. However, with this information gathered here, we can go on to calculate the force of thrust on the car using Newton's second law. The mass of the car is 1.457 kilograms and the acceleration of the car is 7.67 meters per second squared. The final thrust that comes out to be is 11.17 newtons. This is 11.17 newtons of constant thrust on the car. Okay, so it's time to come to conclusions, and we've broken it up into three parts: the mass, the acceleration, and the thrust of the car, and how all these three things interrelate. So, as the mass of the car increases, so the acceleration of the car decreases, which makes sense. As you add more weight to the car, the slower it's going to pick up speed. However, as the mass of the car increases, the thrust of the car also increases. We did not anticipate this to happen, as we anticipated that the thrust of the car would remain constant because we're using the same rocket engine on every car. But our calculations led to the thrust increasing.
For this lab, our sources of error were 1. The camera positioning, and 2. The makeshift car we made. The camera positioning was a problem because the angle we recorded the car with was insufficient for a tracker to pick it up at all times. Also, because of the vertical point of view, depth perception was a problem and tracker couldn't set a correct distance from the beginning to the end. An easy fix for these problems would be to record it from a horizontal point of view so the car travels left to right on the screen. Now the car was a problem because it wasn't aligned properly, which resulted in the car curving right. This also decreased the overall acceleration of the car. A simple fix for this problem would be to make it more precise and making sure that it was aligned properly.